Recording is rolling. It is Thursday, August 21st. So I know yesterday and past few days been looking at this. You guys remember this trigonometry lab on one side and on the back side are these 10 right triangles. So I'm going to treat this as two separate assignments. Some of you guys are ready to turn this in. If you're not, then have this ready by tomorrow. Now, if you have any questions about this page, some students have been asking about this day, or you can ask each other, y'all have some time. Now, the main thing we're getting towards this car and incline lab. You guys have this table, so it's going to take me a while to explain the setup here and what you're looking for, but that's the main thing. But you guys got the last half of the class today and also all of tomorrow. I'll give you guys time to collect data and draw graphs for your data. Okay. Where you see AP here, just ignore the AP stuff. So I'm not going to have you guys do it. Right, don't worry about that. Right? And tomorrow's going to be kind of a short day anyway, for a couple of reasons. There's a pep rally, so they're shaving a few minutes off each class, and then there's going to be a pep rally about the last half hour of school. Will be tomorrow. Right. So so today's a big lab, big important lab that is going to be relevant to probably the rest of this course, like all the way to May. The concepts from the lab today are going to be relevant. So you guys get these Hot Wheels cars. Actually, where's the setup right here? Start this. Right. So here's this diagram. You guys can see back in the lab area, all those inclines. They look kind of like the setup, right? And okay, here's your car right here. You got a little turbo car. Okay, set this down. If you drop this, it zoom, right, zooms down. I wonder how you can describe that motion through, like through physics or math. Right? Here's your question: what equation or equations could govern the motion of a car rolling down an inclined plane? Let's say pitch some angle theta from the horizontal. Okay? So maybe it's so many degrees. You guys should get probably somewhere about 5 or 10 degrees. That's what everybody's going to get today. And they're all a little bit different, but somewhere between 5 and 10 degrees. Okay. Which you can measure with a protractor, right? Could you guys measure that angle with a protractor? Okay. Or you could also calculate it. So while I'm talking about that angle, so I'm talking about this angle of incline. Okay. You get another view of this. Okay. Guys, if you know the length of this incline, I could call it L or D, but I'll call it X just to match my picture from right. This is a right angle here. And you want to solve for this theta. Because what if you do this? What if I measure this height right here? I get like, I don't know, 22 centimeters or something. I'll call it H, or some height. So suppose I know this height is so many centimeters, and I know the length of that ramp is so many centimeters. Okay. Do you guys remember from the past few days how you can calculate this angle theta? How can you do that? Theta equals what? Inverse something? Okay. No. Okay, close.
Inverse over adjacent.
Huh?
Inverse over adjacent.
Well, okay. Guys, if you wanted, who said inverse sine? Inverse sine? Right. Because guys, if you wanted to do inverse tan, you have to know this distance down here, which I guess you could also do, right? I guess you could break out a meter stick and say, what's this horizontal distance that the horizontal displacement the car moves? Right. But if I played specifically off these two sides, like this height, right, which would be opposite of the angle, and the actual length that the car rolls, which is like the hypotenuse of a triangle, it would be inverse sine. Yeah, so it's inverse sine of, and it goes h over x, like that. Okay. So there. In fact, students have been trying both ways today. They've been using the protractor to get a direct measurement. And they also been breaking out a calculator trying this method. And guess what? It's been the same. So 6 degrees and 6 degrees, getting it the same number. Okay. So you guys can try that too. Anyway, we're going to lock that in place. So once you have an angle, that's not going to be a variable today. Now, in a few weeks, it might be, but not today. Okay. You'll have that. So I wonder how you could describe the motion of the car. Okay. Now, here's maybe another variable that will have to be locked in place. What if you took this whole thing to deep space and we're all just floating around? Guess we're all floating around, right? And I set up this incline and I put the car right here and I let it go. What does it do?
Just hold down.
In deep space. Deep space.
It's the same.
Just kind of floats around, right? It doesn't really do anything. Okay. Okay. What if I take you to the moon that has very, very weak gravity? There's a little bit. What does it do? Yeah, it goes down kind of slowly, at least slower than it would on Earth. I don't know if it'd take a long time, wouldn't it? Right. Okay. But are we all kind of locked in the same gravity field? Yeah, we can't really change that so much. So I think the gravity field would be part of this governing equation, but it's not something we can really like vary in this room. Right? So that'll be sort of a control also. Right? So we've got a couple of controls down. This angle is going to be locked in place. The gravity field is locked in place. Okay. So without a side, I wonder what other variables could you maybe consider or measure that could eventually lead to being able to answer a question like this? What might be a relevant variable?
How wet the road is.
Um, oh, okay. Okay. I think you're getting at like an idea of friction or something. You guys see how these wheels are like very, very, very low friction? Okay. We're gonna say that this approximates a zero friction system or like negligible friction. You guys ever played air hockey? Air hockey? That puck like floats around like pretty much zero friction, negligible. Okay. So what if you tip up an air hockey table and the air hockey puck slides down with no friction? This is basically the same thing. Okay, so we're just get rid of all the friction. Okay. Okay. How about how about this? Do you think this distance the car rolls is related to how much time it takes to go down? Right, and that has something to do with like, again the strength of Earth's gravity field. Okay, so I think I want to measure how far it rolls and how much time. There's two variables that could possibly be related somehow, right? Okay. Okay. So guys, on your table, I have to. Okay, you guys write your name. Everybody write their name right here. All right, so you write your name in the top right one. Okay. When you get back to the lab area, figure out. I showed you guys two different methods to solve for the angle, so save that for a few minutes from now. But how about here? See where it says trial and then unit. So we're going to put a bunch of variables going across the top and the corresponding units right beneath those, so that when you guys start writing numbers, those numbers will have the units attached. For example, x could be the distance the car rolls. What do you think is a good way to measure how far the car rolls? What unit?
Meters.
Meters works, centimeters works. All right, guys, pick your favorite. So either choose meters or centimeters, and it doesn't matter which one. Just as long as you're consistent all the way down. It could be either one. Choose meters or centimeters. Okay. Okay. And did I also say how much time? Time. Guys, what could time be measured in?
Seconds.
Yeah, seconds. Right. You guys have some stopwatches back there. It goes like this. So this right button will start and stop. Start. Stop. That was 1.12 seconds, and then this left button will clear it. Point, then you're back. It's it. Start, stop, and then clear. Set. Okay. Now, especially whenever you're using stopwatch, it's really hard to get it exact. Like when to start the stopwatch and the car starts rolling, and when to stop it and it's crossing the finish line. Okay. So it's a really good practice again, especially anytime you're using a stopwatch in the lab in this class, to take 3 measurements and take an average. Okay. So see how I have like trial 1, 2, 3, 4, 5, 6. Okay. Like the first 3 trials might be like you roll the same distance over and over, like 200 centimeters, 200 centimeters, 200 centimeters. Okay. But you time it, maybe get slightly different times because there's a little bit of experimental error and figure out maybe some random error. Sometimes you're a little slower, sometimes you're a little faster. You guys get that? Okay. You can kind of average it out. Okay. Now, what about the speed of the car at the end? Like going through the finish line. You guys see the speed gate right here? See the speed gate? The Hot Wheels car just fits through. In fact, I think it may have been designed for Hot Wheels cars because it fits right on the track. Okay? So if you turn this on, let's fix that. Right now it's blinking meters per second. Meters per second. So if I start that over again. Yeah. It says 2.58 meters per second. So if the car goes through that fast, it would tell you that really. Guys, do you think I'll turn that off here. Do you think the speed of the car going through this finish line has something to do with like how far it's rolled on the track? Right? Like if it's been rolling further, do you think it's probably going faster? Right. How about this? Right. What if I double the distance the car rolls? What if you let it roll 100 centimeters and the speed's like so fast? And then you double that distance to 200 centimeters. Is the speed going to double, do you think? Or is it going to increase but not quite double? Or is it going to increase but more than double? Huh. I guess any of those are possible, and you're gonna find that out. Right. Or hey, what about this variable time? Because what if you were letting it roll for some time? Let's say it rolled for like 1 second from here to here, and then you back the car way up and let it roll for 2 seconds. Do you think double the time would correspond to double the speed? Or would it be an increase at all? And if it was an increase, would it be double? Would it be more but not quite double? Or would it be more than double? Huh. I guess any of those are possible. You can find out. Okay. Go back to distance versus time. Because if the car's been rolling for double the time, is that double the distance? Or is it less than double the distance? Or is it more than double the distance? If it's been rolling for 2 seconds rather than 1 second, so double the rolling time. Huh. how far does it go relative? Huh. Huh. Right. So we need to tease apart all these variables. So you guys see the big complex question we're trying to answer, right? Now that's a lot of variables. Let me go back to my table here because I mentioned. Oh, guys, what character do you think we're going to use to represent speed of the car?
Flash.
V.
Wow.
Yeah, V for velocity. There you go. Right. Now velocity also implies some direction, but the car is just going forward. So, guys, could that be in either meters per second or centimeters per second? Okay. In fact, I might recommend sort of using comparative units here, like centimeters and centimeters per second or meters and meters per second. You guys get the idea. Right. Ooh, how about this? How about this? Guys, what about how heavy the car is? Could I call that, what do you think starts with mass? Mass. Okay. Now, the blank car is approximately 33 grams. There is a scale back there, but if you just call it 33 grams, if you can't get access to the scale, that probably work fine. But I got a box of lab weights. This one's 100 grams. What if I do 33, 100, and take some tape and tape the 100 grams to 33 grams? Now it's 133 grams. Ooh. What do you think that would do to, let's say the amount of time it takes to reach the bottom? Well, let's do a quick show of hands hypothesis. Okay, so I'll narrow it down to three possibilities. Suppose I increase the mass of the car by taping this on it. Okay, that's going to do one of three things. It's either going to make it zip to the bottom really fast, it's going to make it lag behind and take it forever to reach the bottom, or maybe it would make no difference at all. And if you had a blank car versus a car with a weight on it, maybe they would tie. Okay? How many of you guys think, show of hands here, how many of you guys think that if I tape the weight on, it's going to zip down really fast, make it a really small time? How many of you guys think if I tape on the weight, it's going to go down real slow, it's going to lag behind? Who thinks that? Okay. How many of you guys think it makes no difference in whether I have the weight on or not? It's going to be same time. So I'm seeing votes on every one of those possibilities. I mean, it's got to be one of those, right? And somebody's going to find out today. Ooh. Right. So, you guys okay so far? We got an extended premise here. So, a math could be in, yeah, let's go with grams. Okay. Now, you guys know, of course, the base SI unit for mass is actually not grams. It's actually what? Kilograms, right? Kilograms, right? But today you can just do grams. It's fine because really what I care about is finding proportional changes. Okay, proportional changes. Right. Right. Are you guys good so far? Now you guys know. Oh yeah, go ahead.
Research.
Yeah, go ahead. Now you guys know a really well-designed experiment. You want how many independent variables? One, and how many dependent variables? One, and leave everything else controlled, ideally. Okay. And guys, there's way too many variables here to be juggling. So I have a solution. I'm going to split you guys into different teams. Do you guys see a playing card taped to that bar stool in front of you? You guys see a playing card? Yeah. And it has a suit. Okay. So if let's see where's how to spell that. Here you go. Okay. Guys, if you have the clubs, what I want you guys to do is to change the mass of the car and test how much time it takes. But you'll be locking in, well, everybody's locking in the angle, so that doesn't change it, right? But you'll be locking in the distance. So, for example, you could lock it in at 200 centimeters and just let it roll 200 centimeters every time. But you're taping on different lab weights. You're taping, okay, you guys get that? That's if you have the clubs, okay? So, do you see if you have the clubs? If you know you have the clubs, okay? Because I want to make sure, of course, we cover all the bases, so we'll get all the information. Okay. All right. Any questions about the clubs? If you have the spades, you're going to look at distance versus time, but of course you're going to keep the same mass, so you can just use a blank car over and over and over. And you're just saying, for example, maybe you let it roll 50 centimeters, and then 100 centimeters, and then 150, and then 200. So you're going to change the distance, and use the stopwatch to say how much time does that take. Okay? You see that? That's if you have the spades. Okay? All right. Now, the diamonds or the hearts are actually very, very similar, but they're slightly different. Right? Now, the diamonds and the hearts, both of you guys, I want you to find the speed. You could use the speed gate. Right. Oh, speaking of speed, I almost forgot. There is another way you can find speed. You guys see this right here, this motion detector. Right. If you want to try this, you need your laptop. You can use this USB cord to plug this into your laptop. There's a whole set of those back there, and this should tell you the speed of the car. In fact, it might give you a really nice graph. Now, I usually have trouble getting this to work, so this may or may not work. But if you want to be adventurous and try it, you can. There's a whole set of these back there. But I know the speed gates work. Right. So I'll leave it up to you. So diamonds and hearts can both test speed, but a little bit different perspectives. So maybe we'll start with the hearts here. Because if you have the hearts, I want you to vary the distance and measure the distance, right? Keep track of different distances and what's the corresponding speed, right? Now, do you guys think the further the car rolls, it's probably going to take up more speed, probably? That probably makes sense, right? But again, is it a linear relationship? Let's say if you double the distance, is it double the speed? Or is it something a little bit different, right? And your data will, of course, reveal the answer, okay? If you're doing the diamonds, you'll let it roll for different times, and you'll measure how much time is it rolling for, and what's the corresponding speed. Now, if you're thinking about it, some of these are variables kind of tied together. Guys, if you're letting it roll for a different amount of time, is it also rolling a different distance? Yeah, that would have to be the case, right? Technically, you could do both of these if you have a lot of team members and you keep a track. You could keep track of distances. You could kind of do the diamonds and the hearts together. Okay, right. But hearts make sure you're tracking the distance, and diamonds make sure you're using the stopwatch. Okay, right. That makes sense. Okay. Any questions so far? Questions so far? Okay. So what we're leaning towards is to make these graphs. This is the back side of your table. Do you guys see if you flip your table page over, you guys see 6 graphs? Okay. And I gave you guys the suits. So you know which suit corresponds to which graph or graphs. Right? Because if you have the clubs, which means you're changing out the mass of the car, you'll be able to make this first graph, but only this first graph. Right? If you have the spades, you'll be able to make, of course, distance versus time. Right? But also, ooh, guys, look at this other graph right here. This is interesting. Guys, this is not time down here. This is what? Time squared. Okay. Now, this is an abstract idea. Okay, this is an abstract idea. Why I want you to do this will make more sense after you get the data and after you plot the graph. It'll make more sense. Okay, so for now, maybe I'll leave it sort of a mystery. But if you have that, could you do this if you need to? Could you go time squared, put that in square seconds? If you have to, right? Now, not everybody's going to do that. But if you have the spades, you definitely should. If you have the spade, okay? Okay. Okay. So for example, if it took 3 seconds, 3 squared is equal to 9. So if this is 3, this would be 9. Okay, of course, these square seconds would be the unit. Okay. Okay, you see that? If you have the diamonds, you'll be able to graph speed versus time. If you have the hearts, you can do speed versus distance. But you can also do this last graph, which I've labeled speed squared as a function of distance. Okay. Again, why? It's an abstract idea, but it'll make sense once you see the graph. So if you have the hearts, guys, if you have the hearts, then do this. Do speed squared and put it in like meter squared per second squared. Okay? Can you guys do it? Yeah.
Is the T, is that for clubs?
Yeah. The clubs.
We don't observe.
Yeah. If you have clubs, you're gonna use the stopwatch.
But should I like write the TD squared on the?
Oh, okay. If you have the club, this is the clubs, right?
Yeah.
Then you don't have to square the time. No, okay. Okay. All right. I feel like there was something else I wanted to say. Okay. Well, I guess if I remember it, I can tell you guys back there. All right. So again, you guys can gather your data today. I'll also leave everything back there. You can gather your data tomorrow. If you're stuck on those trigonometry puzzles, then you can have time in class to ask me or ask each other. Right? So there should be a good amount of time between the rest of today and tomorrow to get all your data and make some of the graphs. Now, guys, on Monday, we'll put all the graphs together as a class. So you and your team members might be able to put together 1 or 2 of these graphs. And on Monday, we'll put all the graphs together as a class, and which will allow us to go back and answer this question, which is what equation or equations could govern the motion of the car. So you can predict, have predictive power. You'll say, oh, I know if you have like a such and such degree angle, I can tell you exactly how that car is going to move down that incline. Right. That's the premise. And I will hang up this recording right here, and everything you need is back in the lab area. I'll walk back there and help you guys out.